Okay, so machine learning has been discussed this morning. It is a type of artificial intelligence that provides computers with the ability to learn by example and perform a task without being specifically programmed on how to do it. When you want to apply machine learning or deep learning, we need three things. First, we need an objective. We need to have a good problem, something useful that we want to solve. In medicine, generally, we have a good problem, we have a good objective, but still good to keep in mind that we need something useful. We need data. Typically, we need lots of data, labeled. It has to be fair and representative of the task that we want to solve, we want the model to do. And we need a model to optimize in order to do this. So, for example, if we want to train a model to detect whether a specific image is of a cat or a dog, we need a lot of images of cats and dogs. We need them labeled accordingly. Then we show them to the model, and the model learns how to do this. And then we test the model's performance on a separate set of images that it hasn't seen at all, labeled as cats and dogs. In the same manner, if we want to train a model to detect whether a fundus photo is glaucomatous or not, we need a lot of images labeled as glaucoma or not glaucoma. We show it to the model, we train it, and then we evaluate how it performs by giving it a different set of images. So what does it take to train a model? What do we actually need? We need the machine learning expertise. We need to know to prepare the data, to choose the appropriate architecture. We need to tune the hyperparameters. We need somebody who knows how to do it. And you can think of it as managing the blood after a trabeculectomy. You need someone who knows how to make it work. We need the computing power, and we need time. All of this takes time. So how can we scale this to train more models to detect more diseases with better accuracy and faster? Okay. One very promising technology is what we call AutoML. AutoML is essentially a machine learning model that can train machine learning models, build machine learning models. And as you can see on the slide, this is a comparison of human-crafted models, state-of-the-art, with AutoML crafted models on comparison of the accuracies on an ImageNet image classification task. And as you can see, the AutoML models were better accuracy, and they took less time to build. So AutoML is easy to use. It builds better models faster, and it actually eliminates the need for the machine learning expertise. All you need to have is labeled data. But AutoML does not eliminate the need for high-quality labels. And when we say high-quality labels, what we mean is labels that are representative of the task, that are relevant and useful, and help us answer the question we want to answer. They are consistent. A cat is always a cat, or at least almost always a cat. And high-quality labels come from clear grading guidelines that allow graders to align and give consistent ratings. So when our team first started, the first task they took on was diabetic retinopathy. And one of the reasons they took this one, and Fred already showed this part, but is because the ICDR is a widely accepted severity scale for diabetic retinopathy, which can easily be translated into clear grading guidelines. And even when we have clear grading guidelines, this is what we get. And if you look on the x-axis, these are the ophthalmologists, our graders, and on the y-axis are the cases, the fundus photos. And so each row represents the collection of labels given for a single fundus photo. And as you can see, there's a lot of disagreement. And again, doctors in the room are not surprised, but this, our models need consistent grades. And this ultimately hinders and causes challenges in creating the models. This is what happens when we have clear grading guidelines. What happens when we don't have clear grading guidelines and there's no consensus about disease definition? This is our new rainbow chart for glaucoma. And just to clarify, this is glaucoma risk. There's no consensus around glaucoma. There are many severity scales. There are many opinions, I guess, about glaucoma. We don't agree. And creating grading guidelines for glaucoma is very challenging. As you can see, the only case on this chart that everybody agreed was when there was no glaucoma. So ultimately, machine learning comes down to high quality ground truth. And ground truth comes from doctors. The machine learning part is making a lot of progress, but ultimately, in order for us to create useful, good machine learning models to help us help our patients, we need to align ourselves around disease definitions, severity scales. Us ophthalmologists need to make a lot of work in order to help the machine learnings learn what they need to learn. This goes back to the well-known Norwegian job. If we don't provide high-quality labels, the model won't learn and won't be useful. So, in summary, machine learning is scalable. Ground truth is not scalable and is painstaking. And it's our responsibility as ophthalmologists to work on these guidelines and make sure we create and help us help our patients.